Hello guys, in the previous 4 videos we have learned which types of compounds will participate in geometrical isomerism, which types of compound will show geometrical isomerism. Now it's the time to calculate the number of geometrical isomers. How many geometrical isomers are possible in different types of compound? Here the case of polyenes. Look at here, in case of polyenes, if n is the number of geometrical centers, then when both ends are different, number of geometrical isomer equal to 2 to the power n. When both ends are identical, then number of geometrical isomer equal to 2 to the power n minus 1 plus 2 to the power n by 2 minus 1 when n is even, and 2 to the power n minus 1 plus 2 to the power n plus 1 by 2 minus 1 when n is odd. Now let's take some examples. Compound number 1, molecule number 1. This center is not a geometrical center because the two groups are identical, two hydrogen atoms are identical. So this is not geometrical center. This is not a geometrical center. Only this one is the geometrical center. So two ends are definitely different. So 2 to the power 1, just one geometrical center are there. So 2 to the power 1, that is 2 geometrical isomers are possible for this molecule. In case of compound 2, look at here, these two are geometrical centers, and of course these two ends are same, these two ends are identical. Now n is 2 here, n is 2 here, so n is even. Now you have to apply this formula, 2 to the power 2 minus 1 plus 2 to the power 2 by 2 minus 1. This is 2 to the power 1 plus 2 to the power 0. This is 1 equal to 3. There are 3 geometrical isomers are possible for this molecule. In case of compound 3, this center, this is not a geometrical center. This is allyne system. We have learned that allynes containing odd number of double bonds will show geometrical isomerism. So this is not a geometrical center. Only this geometrical isomer will be shown around this carbon-carbon double bond only. So there is one geometrical center, two ends are different, definitely. So 2 to the power 1 equal to 2 isomers are possible for the compound 3. In case of compound 4, look at here, the compound 2 and compound 4. Actually, in case of geometry, these two molecules are identical. Look at here. Methyl is there, phenyl is there, and methyl is there, phenyl is there. So these two ends are identical, and here also these two ends are identical. So number of geometrical isomer will be as it was in compound 2. This is 3. 3 geometrical isomers will be possible. In case of compound 5, importantly, look at here. These two ends are different. Here it is CH3, here it is Cl. So 2 geometrical centers are there. So 2 to the power 2, this is 4 geometrical isomers are possible for compound 5. In case of compound 6, this is not a geometrical center because 2 hydrogens are identical. This is not geometrical center. These two are geometrical centers. 2 ends are different. So 2 to the power 2, this is 4 geometrical isomers are possible for this compound. Okay, let's take the other examples. Example number 7. In example number 7, there are 3 geometrical centers, number 1, 2 and 3. These 3 are geometrical centers, 1, 2 and 3, and the 2 ends are different. 2 ends are different, so it can't have 2 to the power 3. This is 8 geometrical isomers. I have written the 8 geometrical isomers. This is cis, trans, cis, trans. These 8 isomers are possible for this molecule. Let's take example number 8. Here also 1, 2, 3, three geometrical centers are there, but very importantly, two ends are identical here. So there are three double bonds, three geometrical centers, that is n is odd. So this formula will be applied. So this is number of geometrical isomer equal to 2 to the power 3 minus 1 plus 2 to the power 3 plus 1 by 2 minus 1. It yields 2 to the power 2, this is 4 plus 4 by 2 minus 1, this is 2 to the power 1 equal to 6. 6 geometrical isomers are possible. Let's take some conclusion from here. If the two geometrical centers are two ends are different, then it will have 8 isomers, and when two ends are identical, then it will have 6 isomers. What happens actually? These two isomers becomes identical in case of compound 8. Look at here. This and this. Cis trans and trans cis, these two, and 4 and 6, and these two, cis trans cis. These two compounds are actually identical. We will learn from the structure, from the model. Okay, I can write this isomer cis trans trans. This is your CH3 of compound 8, cis trans trans. This is cis, now it is trans, now again it is trans. This is structure. I can write this one is cis, this double bond is trans, and obviously this double bond is trans. This cis trans form of compound number 8. Let's write the isomer of the isomer 6, trans cis. Here it is CH3. I will write in the trans form. So it is trans. Again it will be trans. Now it will be cis. Now it will be cis. This is trans double bond. This is trans double bond. Now it will be cis double bond. Like this. So this is trans, this is also trans, and this one is cis. Look at here, the model here. Look at here, this is the molecule, this is the molecular model of this compound, exactly this one. This double bond is cis, two hydrogen in the same site, 2 hydrogen in the opposite side, so this double bond is trans, this one, and this double bond is also trans, this one. So this molecule is actually like this. This one is cis, this one is trans, and again this one is trans. Look at here, if you consider this molecule in this way, just reverse your viewpoint. Just reverse your viewpoint, and this one is cis. Exactly, this is the molecule. Look at here. This is trans double bond, this is trans double bond, and this is cis double bond. This one is this one. Exactly this one. This one. This molecule is this one. And if you just reverse this molecule and rotate this one, you will find this one. Exactly this one. So cis, trans and trans. So cis, trans, trans and trans, trans, cis. That is, these two isomers are identical, and in the similar way you can write, you can find the cis, cis, trans and trans, cis, cis isomer are identical. So the molecule 7 has 8 isomers and molecule 8 has 2 isomers less than compound 7. So it can have 6 geometrical isomers. Okay, our last example. Compound number 9. There is one geometrical center, there is another geometrical center. This is again a geometrical center. Obviously, we know the cycloalkene ring it is a geometrical center. Cycloalkene ring is a geometrical center. Around this ring, geometrical isomer can form. So there are 3 geometrical centers. 2 ends are definitely different. So 2 to the power 3 equal to 8 geometrical isomers are possible. Okay, this is all about the calculation of geometrical isomers. Thanks a lot for watching the video. Thanks.